Thank you for the invitation to the talk. So today I'll be talking about some paper that I've written together with two collaborators, so Olga and Mikhail. So actually, I should put this in full screen. That's perhaps a little bit better. So the setup is going to be a little bit similar, though I'm going to try to highlight a lot of differences. Of course, the main difference is the degree. So I hope to convince you that it indeed is kind of a different problem, though with many similarities that we can hope to kind of copy specific methods. So the first goal, or at least my goal, when studying this program, this problem, is to study the actions of absolute Galois groups. So again, this is this idea with Galois groups that not a lot of people might be interested in this seminar, but I hope to make it at least interesting enough. So where does this actually come from? This stems from the 1980s. So back in the 1980s, Odoni was studying a certain problem, and this problem was kind of fundamental work showing a relation between what we call arboreal Galois representations. So just like we saw in the previous talk, arboreal meaning like the tree representation and certain density questions. So the primary aim was a very natural question, that being, suppose you have an integer, perhaps a positive integer, and you have a polynomial. So you have some rule that you assign. So this polynomial has integer coefficients, and you iterate this integer over the polynomial. So you obtain an infinite sequence of integers. How many primes will there be in the sequence? So this is a very natural question to ask. However, it is quite complicated. And indeed, as a matter of fact, even nowadays, we are not really ready to answer such a complicated question, even though the statement is so easy to understand. So Odoni in the 1980s also kind of looked at this and thought, okay, well, maybe we look at a more reasonable question. And that uses the following set. So instead of looking at the primes inside of some sequence, we look at the primes that divide at least one non-zero element in the sequence. And in particular, the question arises what the density is of this set within the set of all primes. So now I'm going to try to relate this to Galois theory, because if we have some element or some prime element that divides one of these elements in the sequence, that means that Fn, so this is my notation similar to the previous talk, where I compose f with itself n times, then of course you get a polynomial. This has a solution modulo p, so in the field of p elements. And because it has a solution in the field of p elements, the finite field extension of the splitting field of the polynomial modulo p, which would be generated by some Frobenius endomorphism, an element of the Galois groups, this will have a fixed point, which would be corresponding to this solution. So using similar methods, you can use what we call the Chebotarev density theorem, which relates this to the density, saying that the density of the set that we want to understand is bounded above by this very neat fraction. And in this way, so this fraction is the numerator is all Galois actions or all Galois elements of the splitting field of Fn, so iterating Fn times, that fix a root. And if we take the limit as n goes to infinity, then we have a nice upper bound. So this is kind of where the Galois groups comes into play. So actually, there's this large black thing in the center. I'll try to move that. Okay, that's fine. So we're going to have a very similar setup as to the previous talk. So we consider a polynomial f. This time we are going to consider a field k, and k, it's not going to have characteristic not equal to 2 like in the previous talk, but it's going to be a number field in our case, because the methods that we use, they specifically make use of some geometric properties of the complex numbers eventually. And we are going to consider a transcendental element t over this number field. Now, using this, we can define a tree. So, for example, consider the map z squared. Okay, we are going to consider cubic polynomials, but this is just an easy example. For this transcendental element t, we have two preimages, the square root of t and minus the square root of t. And we draw an edge between well, they're not directed, but between t and the square root of t, because f maps the square root of t to t, if you fill it in. And in this way, we naturally obtain nth level actions. We get a tree that is infinitely far, goes to the right infinitely far, and the level is just the length of the shortest path back to the root. So again, very natural stuff. And then here comes the kind of abstract kind of notation that I have to kind of define. Otherwise, it doesn't really make sense what I'm talking about. So consider the splitting fields. I promise to keep this kind of notation to the minimum in the following slides. And then we define this quickly k as the union over all splitting fields. So naturally, we obtain an action of the Galois group on the set of solutions. So this is almost by definition of the Galois group, though not really by definition, but you very naturally obtain such action. And as a result, you obtain an action by this kind of Galois group of this quickly k over kt. And so perhaps I should justify, if we have an action on the nth level set, so on the root of the solution where we take some n, then that boils down to a natural action on the set of solutions of fn minus 1. So this kind of action boils down very neatly. So in particular, we obtain what we call an arboreal representation. So I'm going to show you in a second more grounded example of what these automorphisms of the tree T that we just defined would look like. But for now, we just get some arboreal representation. And then the idea, of course, just as we saw before, is that we want to understand the image of this arboreal representation. So the profinite arithmetic the profinite arithmetic iterated monodromy group. Now, these groups are a bit complicated. So it could be worth it to first look at what we call the profinite geometric iterative monodromy group. And the groups are very similar. The only difference in this case is the ground field. So here we have just K, and here we have L, where L is the intersection of the separable closure of K with this squiggly K. So the union or the direct limit of all these splitting fields. And we have some benefits. So we have the geometric group canonically identified with a normal subgroup of the arithmetic group. Now, this, of course, on its own doesn't really say much, but, well, perhaps in the future that might be very useful. The geometric group has already been used in various circumstances to determine the arithmetic group. I will give you a very explicit example that was given by Pink soon. I'll also praise Pink a bit, as you will see. And the geometric group, or this is the most important part, in our case with this number fields, the geometric group can be determined by the complex dynamics on the Riemann sphere or the complex plane, including infinity, however you want to identify it. Okay, so now I'm going to be talking a bit about Pink, and after that I will leave the quadratic case and go over to the cubic case. So Pink in 2013 studied and provided details for these computations. perhaps it's a bit of overkill to go over these. I'm now thinking, because we already kind of talked about it before, but I'll go over them anyways. So he showed that these groups are up to conjugacy determined by the conjugacy classes of generators. So this was I think it was called rigidity in the previous talk, and it's also called rigidity in the paper, I believe. And these properties of the geometric group could be used to determine the arithmetic group. So this is where I talk about the examples. So the examples, one very standard example would be if your geometric group would already be equal to the entire automorphism group, because then the arithmetic group cannot grow. So the automorphism group of the entire tree, of course, containing both of these groups. So, and the geometric group is a normal subgroup of the arithmetic group. So if the geometric group is already equal to the automorphism group, then, well, nothing can happen anymore. So we are going to be studying these geometric groups in the case when f is a cubic polynomial. In particular, we will consider a very specific condition on this polynomial because we still want this nice, we still want to have some nice properties that this polynomial might have. Okay, so let's talk about the automorphism group. So in our case, we have a ternary rooted tree. It's slightly more scary than the binary rooted tree. From the start up, this is just a graph. So it's an infinite graph. It goes down infinitely far. Each node has what we call 3 children. So the 3 children are the nodes directly underneath it in this picture. You can define that more formally using this level set. And if we are talking about an automorphism of a graph, we just mean a projection of the vertex set that preserves adjacency. Now, what we also know from automorphisms, or what you can prove, is that they preserve the degree of vertices. So since the root, the top node, is the unique vertex of degree 3, it must be fixed. And therefore, if we look at the children of the top node, they must be permuted because of adjacency of any automorphism. Now, also using this adjacency, we can look at the 3 subtrees that kind of dangle underneath these 3 children. And the subtrees that I've highlighted here in different colors are on their own, because they're infinitely far, they're isomorphic to the entire tree that we started with. So what we are actually kind of setting up here, or what I'm trying to go to, is that if we have any automorphism G of the tree, then it is uniquely given by some permutation of the children of these nodes 1, 2, 3, and some sections, as we call them. So a triple of automorphisms. And this is usually how we denote it. So it's something we call reef recursion. So this gives us a natural identification, of course. So we have a triplet of the automorphism group, semi-direct product with the symmetric group on 3 elements, and a natural notation for this is this kind of sideways tilde. Just means the reef product. I've written a semi-direct product, so I should define the semi-direct product. It's just the symmetric group acts on the children, so it acts on the copies of the automorphism group. Now this is, if you pull this argument through, it's an infinite reef product of the symmetric group on 3 elements. There are more ways of defining this, but this seems to be the most used one. Sometimes authors put it in the other directions, depending on whether you use left or right actions. For now, you don't really have to worry about that. I'm not going to be talking about any of that. What I am going to be talking about is some more properties of this automorphism group. So first of all, if we have any automorphism, then the 3 nodes, the children, aren't the only nodes that have a tree dangling underneath them that is isomorphic to the entire tree. If you go to any node, for example, you follow a specific path in the tree, given by any word. So in this case, we have the word 3, 1, because we go to the right to follow the label 3, and we go to the left to follow the label 1. Then at any node, we obtain, by this adjacency, a new automorphism of the entire tree that hangs underneath it. And this is what we call the section of G, and this is denoted by this restriction notation. So I'll give you one more fact of the automorphism group. So there's a natural metric on this tree. You can think about this by taking two automorphisms, then any automorphism acts on each level in some way, and you choose the first level, if these elements are not the same, you choose the first level where these actions do not coincide. And then you define their difference to be 3 to the negative k, for example, where k is the first level where they do not coincide. And this will give you a metric, and this metric will be compact. So it's a very nice space. All right, so let's go on from these automorphisms and go back to the complex dynamics that I was talking about. So we consider any rational map, so that being a map or a fraction of polynomials. And we and consider the critical set, so just the set of where the derivative is 0. If you're looking at infinity, you just have to take a local chart. Now, we define P of f as the strict forward orbit of the critical set. So these are, you just take your critical points, take the forward orbit, and then we define the ramification index to be, at some point P, to be the multiplicity of the 0 of f of z minus f of p. Of course, if f of p is equal to infinity, or if p is equal to infinity, perhaps even, you have to take into account that you need to take a local chart. But after this is all preserved by local charts, so this is a very natural definition, and it leads us to the definition of a ramification portrait, that being a directed graph with vertex set being the critical points and the post-critical points, where we draw exactly the ramification index amount of arrows from one point to its image. I must add that you can show very easily that there are only finitely many points for a rational map that have a ramification index that is strictly greater than 1, and for all other points, the ramification index is going to be exactly 1. That is, your map is locally a homeomorphism. So I'll give you an example, and this is going to be an example of a ramification portrait of a post-critically finite polynomial. So post-critically finite was already defined before, but I'll talk about it again. It just means that this set P that I wrote above is a finite set. So equivalently, this picture that I'm drawing right here is finite. So this is the cubic polynomial minus 2z cubed plus 3z squared plus a half. Basically the most complicated polynomial I could find where the coefficients were still in Q. The most complicated cubic post-critically finite polynomial where that I could find where the coefficients were still in Q. It has 3 critical points, 0, 1, and infinity. And, well, infinity is always a critical point for any polynomial. The ramification index of infinity is also always going to be equal to the degree of the polynomial. So that's a very nice condition. And now I'm going to be giving you the assumption that we are actually working with. So this is going to be assumption y. And that is, we are only considering those cubic post-critically finite polynomials such that the ramification portrait has exactly 1 vertex with 3 incoming edges. So because it's a polynomial, this point is going to be infinity. Note that this example does not follow this rule. So this is not a valid polynomial for our assumption. Why you might think, okay, why is it called assumption y? And the idea is, well, a y looks a bit like 2 incoming edges and 1 outgoing edge. So I think I actually like the notation. I think it's a very natural way of talking about this. So you'll see in a second why what we actually obtain using this assumption y and why this is actually interesting. So for now, let's talk about the group generators. So as noted before, the generators that we get are associated to each postcritical point. So this works in the same way. And the geometric iterated monodromy group that we obtain is what we call the topological closure of these generators. Topological closure meaning include limits. We know that the automorphism group is a compact group, so limits are a natural thing to consider, and just consider or take off the limit points. Now, each of these generators GP can be explicitly computed using the monodromy action. Technically, an iterated monodromy action. You just have your loops. You kind of punch out all the ramification points of your sphere. Then you pull back your map F. Your loops pull back, and these loops give natural actions on sets of pre-images. Then you just iterate this process. So if we iterate it again, then we naturally have an action not only on the pre-images of F, but also on the pre-images of F after F, etc. Just do this infinitely many times. However, such computations can be a bit tedious, especially if you're working with this very explicit notion. If you're just looking at one polynomial, it can be a lot of effort, especially for what you're kind of getting out of it, or at least in my opinion. Maybe I'm not the most knowledgeable about how efficient this can be. But we're going to be looking at it in a slightly different way anyways. Namely, we're going to model these generators by choosing very nice conjugates. So what I mean is something I'm going to show you using an example. So consider a cubic rational map. So this is just a general example. With some point P in a postcritical orbit. And it has two pre-images, Q1 and Q2 by assumption, Qi having ramification index I. Now, you can show that in this very case, so this is a snapshot of the ramification portrait, that this element GP of the geometric group is conjugate in the automorphism group of the entire tree to the following elements where we have in this recursion where we have some GQ1, GQ2, and then this weird one is the trivial automorphism. And then the first level action being 2, 3. So how do we look at this? How would this work in general? Is the idea comes from that we look at the pre-images, we write those pre-images out in the sections. So in this case, we have GQ1 and we have a GQ2. And then we look at the coordinates that they inhabit. So in this case, GQ1 is in the first coordinate. And since the ramification index of Q1 is equal to 1, we need a 1 cycle on the first level that has support in the first coordinate. Now we have GQ2, and Q2 is has ramification index 2. So we need a 2 cycle on the first level that has support this second coordinate. And also this support does not have any other of these generators in there. So we cannot have GQ1 in the third coordinate, for example. Now, of course, if the GQI or if QI is not in the postcritical set, then these generators are trivial by definition, and this just works fine. So this is how you would do it in general. And if you do this process more generally, then if you have these Y-restricted polynomials, you get a very explicit system of generators. So I'm not going over these conditions very explicitly because I think that's perhaps not really worth your time, because I'm not going to be talking about them too much, not about these specific forms. I am going to be talking about these generators. But if there's anything you can take away from Y-restricted model groups, is that each of these generators will always have one section of which the coordinates is not in the support of a non-trivial first level action. So if we look at the first generator, for example, the third section is trivial and 3 is a fixed point of its first level action. And this holds true for the CI as well by the conditions that I wrote underneath. Okay, so now I have defined model groups where, perhaps I should have said this before. Sorry. So we have this conjugacy of generators of these GPs, but we define these model groups by assuming that these conjugacies are equalities instead. So it's basically the nicest case that you could get. And that's why we call it a model group. So it's just the nicest way of understanding them. And I need to give you some reason for as to why these model groups are actually modeling something. It wouldn't even make sense if, for example, the geometric group would have nothing to do with these model groups. And that leads us to the idea of invariable generation. So suppose you have a group and it is generated by a number of generators, and you twist one of these generators. For example, you have a free group on two generators, and you conjugate one of these generators by a very long word. Now, generally, you do not get the same group back. You get a smaller group. And then the idea in this case is to show that our groups are actually invariably generated, meaning that if we have some set of generators and you conjugate one of these generators by something, the group doesn't change. And I wrote topologically in brackets, meaning we include limits. It's just to make sure that everything is well defined. Now, back to the quadratic case. So in 2013, of course, in this paper by Pink, he considered the geometric groups which are Pro2. So this means that they are an inverse limit of two groups. Two groups being groups, finite group. Well, in this case, there were finite groups in which each element has power an order of 2. So because this is an inverse limit of two groups, it is an inverse limit of nilpotent groups. And what do we know of inverse limits of nilpotent groups? Well, any of these groups is invariably generated by any set of generators of this group. This is a highly non-trivial fact, I might add. I was actually very surprised when I first saw this, but I think it's a very neat result. And as a consequence, Pink can show immediately, using very little arguments, that if you just take the GPs, you don't even need the GP where P is equal to infinity. You can leave that out. You obtain an invariable generating set. So we leave P is in infinity out, but GT infinity is, of course, generated by the other GPs. So what happens in degree 3? Well, something different. Because our groups are no longer Pro3. And Pro3 groups would, of course, lead to this nilpotent property, but that's sadly not what we have. An example is the one on the left. So these elements on the left you could technically call them Pro2 elements. Of course, you would have to define that in a certain manner. And if we take the group topologically generated by A and B, so this group would actually come up as a Y-restricted model group, then this group is not even topologically invariably generated by A and B. One way to see this is that A and B are conjugate. You can flip the entire tree, and A maps to B, B maps to A. This is just one form of conjugation. So if G were invariably generated by A and B, that would mean that G would be invariably generated by just one of these guys, and that is not true. For example, the first level action is already equal to the entire S3, and since the symmetric group on 3 elements is not cyclic, it is not invariably generated by one element. It's not even generated by one element by definition of not being cyclic. Okay, so how do we kind of fix this argument? So we consider the first n levels of the tree. So we denote it by Tn, and we will find an invariably generating set for our group restricted to the first n levels. So this is going to be some induction for this very specific example. So how we denote this is by restricting our elements A and B to the first n levels, and then their sections will of course be restricted to the first n-1 levels. And similarly, Gn is just the group generated by A and B restricted to the first n levels. Of course, this is a finite group, so I can get rid of the double generating brackets because, well, it's the same. And we note the first point about the symmetric group on 3 elements, and that is that it's invariably generated by any 2-cycle and any 3-cycle. So because this is true, we can try to apply a similar reasoning. We'll try to apply something else. And as you might note from the generators that I've written above on the screen, they introduce a 2-cycle to each level. So perhaps for some induction reasoning, we would need to introduce a 3-cycle to each level. And as it stands, there is actually a very natural object that could fill that role, and that is the use of an odometer. So this odometer, so to those who don't know what an odometer is, the idea is a counting machine it depends on what prime you're working over. I guess it doesn't even have to be prime. But the idea is you count in words over the alphabet, in our case, over the alphabet of 1, 2, and 3. So if you have some word over the alphabet of 1, 2, and 3, and you look at the first letter, if it is a 1 or a 2, you add 1 to the first letter, and then that's your image. If your first letter is 3, then you change it into a 1, and you go over to the next letter, and you repeat the process. So that is what the odometer does to these sets of words, and that is how people often look at these odometers. The odometer, as written or shown in this picture, is often what we call a standard odometer, though sometimes people write the G on the left side. Or if you want to be really crazy, you can even write it in the middle and call that the standard odometer, but I don't think a lot of people would do that. In any case, in our case, you can prove that B times A inverse is equal to G. But again, this is not very trivial. You can show that Gn is invariably generated by A restricted to the first n levels and B times A inverse restricted to the first n levels. So we have, in fact, been able to use induction, or this induction step, using some odometer, using this invariable generation of the any 2-cycle and any 3-cycle in some way to show that we have invariable generation of Gn. This is slightly oversimplification because, of course, Gn is not equal to the entire automorphism group, not in general. So you have to be a bit careful here. But this is the idea behind it. And then if you take an inverse limit, you just throw n to infinity, you get invariable generation of G by A and B A inverse. So that's really nice. We have found some invariable generation. But that's, of course, a very specific example. And now we have to kind of do this in general for any y-restricted monogroup. And as a matter of fact, you can still do this. So if you have any odometer G in your group, you can just take G together with your generating set, and you get a topological invariably generating set by this set S. And that's it. So we get invariable generations, exactly what we wanted. So that's great. I might oversimplify this a bit, of course, just like I said with the example, but the idea is very similar by using this induction argument. You might also ask, okay, but what if we don't have an odometer in our group? Well, you always have an odometer in this model group. One way to go over this is by some work of Nekrashevich. You can show that the generators that I've written above here form a kneading automata. And because of this, if you multiply these generators in any order, where we take each generator exactly once in this product, then we will always get an odometer. So as a matter of fact, we have lots of odometers. So that's great. As a matter of fact, in this product, you can even change one for the inverse of itself, and you will still get an odometer. So that's a very nice way of going over this. Now, I have made things even more simpler than as simple than perhaps is true, because I have used invariable generation within the model group. So of course, if we have our elements from the geometric iterated monodromy group, if we have our generators, they are conjugates of these model generators, but we don't know what they are conjugate by. It will be some automorphism. We don't know if this is from the model group. So what if we conjugate some of these generators by some other element? Well, in that case, well, let's just write it down. So we have these Wx, where X is any generator, and we look at the topological group generated by these elements. So the idea here is that this could, for example, be our geometric iterated monodromy group, and we assume that it contains an odometer. Now, this might be a strong assumption in the general case, but for the geometric iterated monodromy group, because it is a polynomial, you can show that indeed it contains an odometer. So this assumption is perfectly satisfied. So that's exactly what we wanted. And now using more arguments, so this is a technique that is very similar to what Pink used in his work. You can show that there exists a single W, a single automorphism that conjugates each of these conjugates back to a G conjugate of the element that we started with. So back into the model group, and also in the model group, it will be conjugate to the guy that we started with. And that is amazing, because if that is true, then immediately by the invariable generation that we just showed, we get the entire group. Wait, I need to move this. Yes, just making sure that I didn't miss anything. So exactly, so conjugating it by this W, okay, we don't know what W is, we get the model group back. So this means precisely what you might think that it means. That being said, that that being that the profinite geometric iterated monodromy group is always, in the Y-restricted polynomial case, going to be conjugate to some model group. So if we have any Y-restricted polynomial, whatever we end up with, we can model it. Perfect. That's exactly what we wanted. Now, this group G, as you might have seen or might have noted, it's determined entirely by the isomorphism class of the ramification portrait. Because of this conjugacy property, you only cared about what the ramification portrait looked like, just the graph properties. So that makes things a lot easier to compute. So in particular, to kind of summarize everything that we have done by now, we obtain that the profinite geometric iterated monodromy group is topologically finitely invariably generated by the set of standard generators. And perhaps it is good to put some emphasis on this. If we have any other polynomial that has an isomorphic ramification portrait, the associated groups, the associated geometric groups are conjugate because of this conjugacy to the model groups. And well, in my opinion, this is a very strong result, and it's actually a very nice way of putting that down. But in any case, now we know the geometric group is conjugate. Now that we know that the geometric group is conjugate to some model group, we can just study the model group, and perhaps we gain more insight about the structure of this geometric group, which in the end we actually want to know. So I'm going to highlight some similar work. So first of all, more generally, we have this paper by Adams and Hyde, which was posted to the archive in 2025. It was also noted in the previous talk. So they studied the same problem in this case, for unicritical polynomials. In their case, they obtained similar conclusions. You have the similar kind of nice identifications. The generator G infinity is not needed for invariable generation. So perhaps I've hit this a bit. We technically use the G infinity for invariable generation in the sense that we use an odometer. So G infinity in our case corresponds to an odometer, and that's why we technically need it, because we needed an odometer for the invariable generation. And actually, perhaps I could have rewritten this just between the previous talk and in this talk, because also what Jamie described was something very similar. But the idea is that you can do everything over more general fields. I think that our work can also be generalized over more general fields. And then in our case, you would only consider fields that are co-prime to 6. Because I think you need to take things that are co-prime to 6, because you have things that have ramification order 2, which might pose a problem, and things that have ramification order 3 that might pose a problem. And now to kind of highlight that we are actually doing different work, and we're kind of strengthening each other's results. If we have any polynomial that satisfies assumption y, then it's not unicritical, and vice versa. So it really is some nice other kind of piece of literature. Okay, so now I am going to use this remaining couple of minutes to talk about our results. So I hope I haven't lost you at this point in time. Perhaps I've gone over it a little bit slower than I initially hoped. But in any case, I'm going to define one more thing, and that being branchness. So this might look weird to people who haven't seen this Reef recursion notation before. Of course, recall that we had, for each automorphism, we had this notation where we had 3 automorphisms acting on the subtrees. And if you kind of visualize this, though I'm speaking from a point of having seen these groups many times, so it's a bit unfair, but we obtained something that could look like this very weird inclusion, where you have the group, you take the product 3 times, and then it is included into the group. But anyways, this is what we call a regular weakly branch group, if your group contains such H that is not trivial. If this subgroup H is finite index, then we say that it is regular branch. And now in our case, with any of the Y-restricted model groups, this is true for all of them. If you compute this group C, or this very weird, I believe it's a math frac notation in LaTeX, to be the closure of the commutator group, then you can see that, well, first of all, we have shown that G is regular branch over C, that meaning it has finite index. And of course, C contains its like copies of itself, so that's very nice. Moreover, you can show that C contains an infinite Reef product of the alternating group on 3 elements. So if you recall that the automorphism group was an infinite Reef product of the symmetry group on 3 elements, you might see, okay, well, that means that C is already quite large, whatever that means. So perhaps this will help us with some kind of identifications within the arithmetic group. Of course, I don't know for certain, but perhaps there's something there, because it is already that large, or perhaps I'm talking complete nonsense about that embedding. But anyways, using this iterated Reef product of the alternating group, we can talk about torsion. Namely, it immediately follows that C, and therefore also the model group G, contains any element of order 3 to the n. I should rephrase that, because that's not true. If you have any order 3 to the n, then it contains an element of that order, not the other way around. So you can ask yourself, okay, what orders are we missing? So suppose we have any torsion order or torsion element of the automorphism group. Because it's an infinite Reef product of the S3, any element must have, or any torsion element must have order dividing 6. And therefore, any torsion element must have order of 2 to the n times 3 to the n for some n and m. And indeed, for our model groups, these orders are also realized. So let's quickly go over how we can find this. So first of all, using the branchness we can find any element of order 3 to the n and put it into this form. Or we can find some element of order 3 to the n and put it into this form. And we can also show that we can always find an element of order 2 to the m specifically of this form. We can always put it into this form. And then if you just take the product of these two guys, then you obtain an element of order 2 to the m times 3 to the m. So the reason these orders don't really overlap is because they commute, which you can see because the h is in the third section and it's not in the support of the first level action of the other elements. And then the order naturally follows. All right. Then, of course, because these model groups are conjugates to the geometric iterated monodromy groups, these geometric iterated monodromy groups have the same property. We can always find any torsion order. So that's perfect. So then I'm going to talk about one more result, and that's going to be about group filtrations, which I think is a very natural kind of last question to ask. So I was talking about if we have two polynomials f and f prime that have isomorphic ramification portraits, then their model groups or their geometric groups are conjugates. What happens if they do not have isomorphic ramification portraits? Can we still relate them in some way? And the answer, perhaps, it is not completely clear, but as a matter of fact, in some cases you can compare them. And one example is in the following model. In the following model. So the idea is, suppose you have a model, two model groups where one which are given by two cycles. So of course they were given by the ramification portraits, and these cycles of the ramification portrait. So we have two finite critical points, and of course a critical point at infinity. The two finite critical points are cyclic. Of length, the cycle has length m1 and m2 respectively, which of course will give us a model group. Then you can see that the model group CC 8,8 contains the model group CC 4,4 strictly, and this equals the model group CC 4,1. And of course, okay, this equals CC 1,4, but that's I guess a bit trivial. So the way you can see the equality of CC 4,4 with CC 4,1 is by conjugating the 4 cycle into the 1 cycle, and you obtain several elements. But the first inclusion is indeed strict, which I will show quickly, and I think that will be the last thing that I will show. And that they are strict kind of shows that indeed we have some, that if you kind of zoom in on these orbits, you obtain more complex, more interesting groups. You kind of filtrate through them. I think I can quickly show this. And then the main results, I guess, is a bit too much to talk into 2 minutes. So let's talk about why this inclusion is strict. So we define these epsilon k's where we just take the product over all the signs of all the sections of words of length k. So this is quite a lot of notation, of course, but with the sign of some section, I just mean the sign of the first level action. So this is going to be the sign of some element of the S3. Then I define this epsilon by taking epsilon 0 and epsilon m. And then you can show that very quickly that CC m, m has image of 2 elements, and epsilon of CC nm, nm has an image of 4 elements. So this is one way of showing, okay, this inclusion is indeed strict. And there is a general result. I'm going over this quicker than I intended, sorry for this, but the idea is there is some conjugacy in the general case when we have disjoint critical orbits. So that's very important. If we have disjoint critical orbits, then we can say a little bit more about this, where we want the pre-periodic part to divide the pre-periodic part and the cyclic part or the periodic part of different of the other map, or of the critical orbit of the other map F. Yes, so I apologize for this last slide. I have to keep this a little bit short for time sakes. But if you take anything away from this, just know that there is some conjugacy and inclusion happening there. So that is great, and I will leave you with two open problems. So one of them being, if we have an arithmetic group or geometric iterated monodromy group associated to some postcritically finite rational map of some degree greater or equal than 3, are they always finitely invariably generated? As a matter of fact, I believe this is perhaps not true. I think this is perhaps a bit strong if you go to higher degrees, but it's always interesting to figure out, and perhaps there's like some standard or canonical generation. And the other problem is, suppose that you have any rational map of degree greater or equal than 2. Is the Profinite geometric iterated monodromy group always determined by the ramification portrait of F up to conjugation? Because this is such a strong concept. Okay, I apologize for going over time slightly, but thank you for listening.
Yeah, thanks a lot. Let's thank our speaker. And let me start the discussion. So comments or questions?
Yeah, maybe Dean, let me ask you a question. So sort of inspired by the previous talk and by Richard's work as well, do you know if the sizes of this groups GN could be computed? So like if you restrict to the particular level, can you compute the size of the restriction depending on the ramification portrait?
Oh, depending on the ramification portrait, that's very interesting. Okay, so I have to be honest, I haven't thought about that. So in general, you can, of course, kind of give some vague idea of how large they are. Depending on the ramification index, I would be very interested to think about that, but I do not have an answer right now. I would say that there's not, it's not like there's no hope, because of course they are determined by the model groups, and they of course are determined up to conjugation by these ramification portraits. So in some sense, of course, this is true, but whether there is like some natural way of seeing this, I do not see yet. Sorry, no.
Let me ask you a question that is related. I mean, can you say something about the growth behavior of the groups?
Yes. So okay. Yes. So these groups they grow, of course, very fast, and I guess my answer is going to be very similar to that of Jamie, where we have infinite index in the automorphism group, but this basically just follows from the polynomials having or being postcritically finite. Then and what the exact growth is, I guess that's, yeah, I don't know whether it depends, but that these groups always contain this iterated product of the alternating group. Yeah, so whether they or because they contain such an iterative reef product, that's already very strong, and it might indicate that we have some very strong growth going on there. So yeah, I don't think I can say much more about it than that. Sorry.
Maybe let me comment a little bit on this. So Mario, I mean, because here you consider like so these groups are being topologically generated. So these groups are the closures of the discrete iterated monodromy group and the holomorphism of the tree. So basically, the right way to ask the question about the growth of this group is basically what I kind of originally asked. So this is actually something which kind of people compute for this group is something that's called like how's the dimension for this group. So you look at basically kind of proportion of elements when you kind of restrict on the nth level that you see. So that's kind of that's sort of the natural way to ask the growth questions in this case.
Yeah, I see. Okay, so do we have other comments or questions?
I'm wondering if you can give a little bit more intuition about where this y-restricted model comes into play. I know that you need to be a polynomial to have like an odometer, but what does the extra condition give you?
Yes, so I glossed over this actually. If you go to the model generators that we have, we used something that I did not actually talk about. If you so of course I said that they all have like a trivial section, and the first level action does not have this trivial sections in its support. And you use this to kind of force the induction step. So because we have the generators A, B, and the CI in the sections, you use this trivial section to use to take conjugation to the previous level. Okay, let me see how I can rephrase that a bit. Yeah, okay, so suppose we have like some elements x comma 1 comma 1 and then 1 2 on the first level action. If we square this element, we obtain the element x comma 1. That's the automorphism that we obtain. Now, if we, for example, had an element of 1 comma y in the same manner, or sorry, y comma 1 comma y in the same manner, then conjugating this first element by this latter element would give would conjugate x in the first section by y. It would keep the second section as it is, and the third section would also keep it as it is. So the idea is that we can conjugate one section at a time by any of the generators, and that's why the model groups are so nice. Yeah, so it is just this induction step that you kind of want to get, and this conjugation that you want to do one at a time in the sections. I hope that kind of makes a bit sense. I know it's perhaps a little bit too much in my head.
No, that's great. Thanks.